I've replied back to most emails. I got through an awful lot this weekend, but I'm still working. If I had paper copies, I've gotten through all paper copies of stuff. It doesn't necessarily mean I've put it into Blackboard yet, because I'm going through and making sure that I don't have that I haven't missed it somewhere. So I'm getting there. I'm getting caught up. I spent quite a bit of time this weekend getting caught up, but we're moving on. We're keeping going. All right, so I've got the record on, and we should have the document camera going forward. So hopefully you can see the document camera over there, Enid. All right, and I know I lost you guys right at the end. I lost Tonkawa right at the end, so you guys are the ones cut off this time. And we were talking about projectile motion, or at least introducing projectile motion. I am in the process of getting that video uploaded to YouTube right now. Something funky happened earlier. So we are starting chapter 4. Goody. And as I said on Friday, because we're starting chapter 4, we're targeting the test next Tuesday or next Wednesday. And that's February 11th. It's the 13th, right? February 13th. All right. You'll be allowed an 8.5 by 11 sheet of paper with anything that you want written on it. Needs to be in your own handwriting. Okay. So you can put sample problems on there. You can put equations. You can put a variety of different things. It will cover chapters 1 through 4. I wanted to get us through projectile motion before we start moving in. I have also posted, as of this morning, the lab for next week, and we will not have time to start the material for the lab next week because it's going to be Newton's second law is what you're going to be doing in the lab. But we won't have started, I don't think, well, we might start it on Friday, given where we're at, but because I'm going to work some more problems in terms of projectile motion, and we're going to start a little bit of motion in the circular dimension today. So we're actually in pretty good shape for where we are in the semester, and I'm trying to get everything into the stuff. I sent an email out to a couple individuals, so definitely check your email, because I got all the WebAssign. I got several WebAssign things into Blackboard. So if I've messed up the typing, or you thought you did it and I didn't do it, and so it's through like last week, like last Wednesday. So the things that may have a due date of after last Wednesday may not be in WebAssign, or that were in WebAssign may not be in Blackboard. I will do a quiz this week, so that you guys have a chance to see sample questions for projectile motion and two-dimensional motion, so that you'll have that to kind of help. So from a logistics point of view, we're good. All right. So where we were on Friday, as I had drawn my lovely little cannon, and we were talking about how we know that our motion, we're going to hit the target, and we have some parabolic motion associated with it. Some interesting things about this, we can always write a position vector, because that's what we've been doing with vectors. We can always write a position vector that says R is equal to something in the X direction, something in the Y direction, and if I want to do it in 3 dimensions, I have something in the Z dimension. So I can have a 3-dimensional vector. Now when we do our special case of projectile motion, usually all we're doing is 3 dimensions. And so we're not worried about the Z. And when we do our projectile motion, we're usually doing it in the Y, X direction. And we have our coordinate system like that. But if I'm doing my 3-axis coordinate system, which is what we were talking about on Friday, X is usually out of the paper, Y is across the paper, and Z is up. And the reason we would do that is we started talking about a right-hand rule. Started looking at that right-hand rule. So we can look at our position vector. And then I can do my change in position vector, which is my displacement. And we know that this is going to be x final minus x initial times the I direction plus y final minus y initial in the j direction plus z final minus z initial in the k direction. And we could even write this as the change in x in the I direction plus the change in y in the j direction plus the change in z in the k direction. And this is what we've done oodles and oodles of times in math class. Without, kind of disregarding why we might do that physically, we've been doing that in math class forever and ever and ever. And we know from the last couple chapters and the fact that we've been playing with it that my velocity vector is going to be my change in position vector with respect to time. And we've even talked about how this would be the derivative of my position vector with respect to time. And basically all we end up doing is we can end up rewriting this. I can do it in a variety of different ways. I can do this as a vector in the x component of my vector in the I direction plus my y component in the vector in the j direction plus my z component in the k direction. And if we did it, if we write it out like this, it's my change in x with respect to time, my change in y with respect to time, or my change in z with respect to time. Or if I write it out in the calculus form, for those of you who've seen that before, I can do it as my derivative. So I can actually do it in terms of a derivative. So we've seen a lot of this in mathematics, but the trick is, okay, how does this really apply? Okay, how does this really apply? What is it that we're actually doing? Why is it that we want to play with it, and where is it we're headed? And I can rewrite these same things for the acceleration, right? And so just so that we have it complete, let's rewrite it for acceleration just so you have it as well. And my acceleration vector is if I write it in terms of the derivative, looks like this, or I can write it in terms of my change of, it looks like that. And then I can also, if I do this as a change with respect to time, this is also a change in position with respect to time. So this is where we get our change, this lovely thing that we do if I'm doing a position vector. And this is what we call the second derivative if I do that. Now that's only in one dimension because my acceleration vector can be written as my acceleration in the x direction plus my acceleration in the y direction, plus my acceleration in the z direction. And that is the more general form. But if I'm tossing a ball, and we're tossing the ball back and forth, right? We're playing catch, and we're tossing the ball back and forth. Once it leaves my hand, so I'm going to have my hand here, so I'm going to draw my little fingers. Once it leaves my hand, there's nothing that's pushing on that ball, okay? Once it leaves my hand, it's been given a velocity, and usually we look at this velocity, so let's say this is the velocity vector that ball has been given. If I look at what's happening in the x direction, there's no acceleration. The acceleration in the x direction is 0. But I do have an acceleration in the y direction, and that's our gravity. Okay? So if I'm looking at this v vector here, we can look at it in a couple of different ways. If I want to write this v vector, I can write that v vector in terms of a vxi plus a vyj, and we've even talked about how I can break those components up. So if I know this angle, this becomes vx is equal to my v cosine of the angle, and this one for vy is equal to v sine of the angle. So when I'm dealing with velocity vectors and I want to start a problem, if I'm stuck, first thing I'm going to do is break it up into its components. Because the things that are happening in the y direction are independent of the things that are happening in the x direction. They're kind of independent variables. We can look at them in terms of an independent variable. So let's kind of play with this for a second. And let's take and I'm going to make up numbers, okay? So I've got a little drone here, right? A little Amazon drone. And the fact that we live in places like Tonkawa and Enid, the odds of Amazon delivering a box by drone for us are slim and none, right? At least for a long time.
Can you pull it down a little, please?
Sure.
We can't see the top.
Okay,
Thank
so
you.
I got my little drone here, right? And it's going to be flying off, let's say it's 10 meters. We'll do 5 meters per second. I don't actually know what the little drones are doing. But they also are not flying too far above the ground, right? So my little drone is flying too far, and everybody's touting. So here's the back of my pickup truck. And we want the package in the back of the pickup truck, right? So they've had to calculate this. So this is a realistic problem. And let's say, for grins and giggles, that this is 10 meters above. So if I'm going to drop that package into the back of the pickup truck, we know what happens if I drop the package, right? What? It's going to fall, right? But the thing about it is it's going in that direction, right? It's going 5 meters per second that direction. So we know what the path is going to look like. The path that we want it to do is fall into the back of the pickup truck. So this little thing is going to have to release the package before it gets to the back of the pickup truck. Okay? It's going to have to release the package before it gets back to the pickup truck. So we know that it's going to end up doing that, and it's got to end up into the back of the pickup truck, so it's got to release it ahead of time. So we can kind of look at this. So we've got some equations that we can play with. So let's look at the x direction. And we look at the y direction. So let's look at what we know. First of all, we know we've got an acceleration due to gravity, right? And that's 9.8 meters per second squared. So we know we've got that. So in the x direction, we have a velocity in the x direction that we know is 5 meters per second. And this is our initial. What's our initial velocity in the y direction?
10 meters.
Velocity.
5 meters.
I've heard 10 meters, I've heard 5 meters, and I've heard 0. How many think it's 10 meters? Good. Because I said 10 meters, right? That's not velocity. That's position. Okay? How many think it's 5 meters per second? I've got some hesitation. You guys over in Enid, how many think it's 5 meters per second? Oh, I got shaking of heads. How many think it's 0 meters per second? Yeah, that's right. It's 0 meters per second. Okay? 0 meters per second, because there's no velocity in the y direction initially. Now, once I drop it, I'm gonna have some velocity, right? Once I drop it, I'm gonna have some velocity. Now we know its initial position in the x direction. We don't know that, right? And we don't even know the final position in the x direction. We don't even know, we don't know that either. We don't know the initial or the final. But we do know our initial position in the y direction is 5 meters. Or, sorry, not 5 meters, 10 meters. No, it's 10 meters because that's how high above the ground that we're flying with the drone. Now, for the sake of this problem, I'm going to disregard the height of the back of the tailgate of the pickup truck. Okay? I'm going to assume that the tailgate of that the drone is actually 10 meters above the back of the pickup truck. Now, we can take that into account, and we can do that with a basketball problem, but for this initial problem, I'm going to disregard that. Partially because I got a good target in the back of my pickup truck. But we know what that change in position is. So if I'm doing this, so I got 10 meters, that's the height. Now, here comes the trick. I don't know time at all. I don't know time at all. And I don't know this distance. I don't know the distance or the time. But I can still figure out the time of when I need to drop the package into the back of the pickup truck. Or at least how far ahead of the time before it hits the pickup truck, I can figure that out. Because I've got that the change in position is equal to my initial velocity in the y direction times time, minus 1/2 gravity times time squared, because I'm dealing with just a gravity problem. Well, my initial velocity in the y direction is 0, so my change in y has got to equal minus 1/2 gt squared. So I'm going to have 2 times my change in position divided by negative g is going to equal time squared. Or I've got time is going to equal the square root of 2, and this is going to be minus 5, or keep writing the 5, minus 10 meters divided by minus 9.8. If I put that in my negatives cancel out, which is a good thing since I'm under the square root. So I got 20 divided by 9.8. This gives me the square root of 2.04, and this is all in, this is in meters per second squared. Meters cancel, my second squareds end up on top. That I come out, I'm end up in seconds. So life is good. And so it's going to have to drop it 1.43 seconds before it flies over the car. And I have to drop it 1.53 seconds or 1.43 seconds before it goes over the car. But now we want to know how far that is. What's the distance? Well, that's easy enough because my distance is going to equal the velocity in the x direction times time. I now know time. I have the velocity in the x direction is 5 meters per second, and I got to drop it at 1.43 seconds. Those cancel out. And it's going to be 7.14 meters. So when it gets 7.14 meters out, it better drop, release, in order for it to hit into the back of the truck. That's if it's going to stay flying at a nice little constant pace, right? That's if it's going to stay flying at a nice little constant pace. But what do we know that the drones do? They go over, they target it, and then they just release it down. But you can do this with parachute drops. You can do it with bombs. You can do it with target practice. You can do it, so, I mean, there's a lot of those little pieces of things that we talk about in order to have it come off the top. So we'll play with that a little bit more here in a second. But let's look at a circular path. because I do like this book because it starts introducing circular motion early. And so let's look at circular motion for a second. So one of the things, ooh, that's bad. Everybody knows that the more perfect you draw a circle, it's a sign of mental issues. And I have a very nice circle today. It's been kind of a long weekend. Yeah. So what we know is if I've got a little bead that's traveling around my circle, if I'm right here and I look at the velocity of my little bead as it travels, that's its velocity vector. So even if it's going around the circle at a constant speed, it's still going to have an acceleration. And that's what we talked about a little bit on Friday. I'm getting an acceleration because my acceleration is a change in velocity with respect to time. And I'm going to write it out in the calculus vernacular as well. So this is change in velocity with respect to time. So because even though it's traveling at the same magnitude, because I'm changing direction, I end up with an acceleration. And we even talked about how that acceleration is actually directed towards the center of the circle. And I'll get some nice pretty graphics to show you where that acceleration is going towards the center of the circle. Now, if I'm traveling at a constant speed, we're going to introduce a value, and it's called omega. And omega is what we call the angular speed. Okay? Omega is the angular speed. So if I'm looking at this, so I'm going to start here at this part right here, and I'm going to go here. If I'm going around a circle, if I'm heading around the circle, it's heading by a different angle. There's my angle, and omega is actually going to be defined as the change in angle with respect to time. So I have something that's around that curve that I'm going to be dealing with. So I can actually look at and these do turn out to be vector quantities, okay? They do turn out to be vector quantities. And another quantity that we'll ultimately see, although they don't introduce it in this chapter, is an alpha, and that's my change in my omega with respect to time. And this is known as the angular acceleration. And this is the angular velocity. Or we can look at it in terms of angular speed if I'm traveling at a constant speed around the circle. Some interesting things when you think about this, right? If I'm on a merry-go-round or if I'm on a carousel, it doesn't matter whether I'm traveling along this arc or that arc or this arc. This line, no matter what I do as I'm going around that pivot point, is always going to be traveling at the same angular speed, right? Because I'm always going to be changing this angle with respect to time. It doesn't matter. Now, the farther away that I am, all right, the farther away that I am, this R is R1, this R is R2, this R is R3. We know what it feels like. Because the farther that I'm out, and if I'm doing roller skating, or if I'm doing ice skating, or if I'm doing horse quadrilles, or I'm in some sort of marching pattern or whatever, this person's going to be having to take bigger steps in order to keep up with this person who's just essentially pivoting around the middle. So there's some interesting things that happen, even though this angular speed of the motion that's going around the circle is going to be feeling a little bit different depending on where you are in that circle. So we have some interesting things that are happening right? We do have some interesting things that are happening, but I'm still traveling at the same angular speed. I still have the same angular acceleration because of how I'm going around the circle. Now, a couple of other interesting things that we can look at. I can represent my motion here, right? Because we can actually look at this. So if I have this angle theta there, my position of this vector as it goes through, depending on where I'm at, is always going to be a cosine of my angle. But look at where my angle is. So if I do omega theta over t, if I'm looking at that, omega times t is going to be equal to my angle, and this actually becomes a cosine omega t. So we can start looking at those individual components. Now this side over here is a sine omega t. So as we go around that circle, we can start representing our angular motion as well. So it's going to turn out that I have kinematics that looks the same in terms of my angular motion as well as my translational motion. They're going to have the same forms when we start working with it. So those kinematics equations, so if I'm making my cheat sheet, right, we all want to know what kind of cheat sheet I'd make for the test, right? If I'm making for my cheat sheet for the test, things that I'm going to put on my cheat sheet are as follows. Because this test is likely to have conversions on it, I'm probably going to have a couple of conversion factors. I'm going to have my 2.54 centimeters is equal to 1 inch, right? I might put on, you know, my 0.62, my 0.62 miles is equal to 1 kilometer. I might have a couple of those just in case I throw you some curveballs in terms of doing a conversion, because you're likely to see a conversion on the test. But I'm certainly going to have that x is equal to the velocity times time, right? Certainly going to have that. I'm certainly going to have v squared final is equal to v squared initial plus my acceleration times time. Nope, wrong one. See? 2a times my change in x. This one's v final is equal to v initial plus acceleration times time. And then I have my change in position is equal to v initial times time plus 1/2 at squared. Now if you want to, you can put these in terms of g and h, because with projectile motion we look at g and h. I mean, we can look at a variety of different things, but this is really pretty much all I'm going to have to use for. I might put some things like, okay, my if I have xi plus yj, and this is my r vector, and I want the magnitude of r, I'm going to probably have my square root of x squared plus y squared, and I'm going to have the tangent of the angle is equal to y over x. And then I probably want to have my triangle just so that I don't get myself confused. And then I can put my cosine and my sine and all of those things in there. So those would be things that I would have on my cheat sheet. Okay, those would be things that I would have on my cheat sheet. But what's really cool about this, one of the reasons that I bring it up is because now let's look at this. So if this is my vector r, so r, we know that r squared has got to equal x squared plus y squared if I'm doing my x and my y, right? And if I look at my vector r in terms of this, I'm going to have a cosine omega t in the I direction plus a sine omega t in the j direction. And the fun part about this is if I want to find the magnitude, I get the magnitude of r is going to be the square root of a squared cosine squared omega t plus a squared sine squared omega t. I can factor out my a, right? So I get the square root of a, and I get cosine squared, there's an a squared, cosine squared plus sine squared omega t. And we all know that cosine squared plus sine squared is equal to 1. So this just becomes the square root of a squared, which is now just a. So that circular motion, we're going to keep coming back to circular motion. And one of the things I like about this text over the old text is the old text would wait until like chapter 7 or 8 to bring in circular motion. And it's kind of nice to start looking at this at the same time before we actually start having to deal with that circular motion for later on. Okay. All right. Let's play with a fun problem so that you guys can start. If you haven't already started your homework, let's play with a couple things that we can have. All right. So I got a cliff here. And off of the cliff, it's a mesa. All right. It's a mesa. And we got good old Wile E. Coyote over here. So we got a rocket. And we're going to start off with a 35-degree angle. So Wile E. Coyote is going to go off with a 35-degree angle. We're going to start with the height of the cliff. Being 500 meters. And we've all watched Wile E. Coyote. Most of us have. First of all, we know this is going to end up poorly. No choice. It's going to end up poorly. No matter how he figures it out, it's going to end up poorly. Right? We know what the path is going to be. Or we know what the path is going to look like, right? Path is going to look like this. And the intent is that we've got our birdseed pile with our free birdseed sign. And we're hoping that the Roadrunner is going to still be there. Okay? We're hoping that the Roadrunner is still going to be there. And so we know, again, we always know that this ends up poorly. So let's start off that his rocket is going to go 100 meters per second at a 35-degree angle. And so we might ask the question, the first question is, how long does the Roadrunner have? Okay, and the reason we want to know that is because we want to put enough birdseed out there so that the Roadrunner is going to stay in the one spot for that length of time. Okay? We're going to disregard a whole bunch of other stuff, like did he set the target right? We're going to come back to that. We're going to set the, but right now we're going to look at how long does the Roadrunner have. So when in doubt, step 1, draw the picture. All right. On my test, which is going to be multiple choice, yes, it'll be multiple choice, but you're going to have room to work out your solution, because I will give you credit if even though it's multiple choice, it's going to make it a little easier for me to grade. I will give you partial credit if you get the answer wrong. I'm going to look at your work. You will get at least 1 point if you have a picture that is reasonable for the problem. So to get a total 0 on my test, if it's worked out problem, is going to be pretty hard, right? Because that just means you just left it totally blank. Next part is, when in doubt, figure out the components of your vectors. So we know that the velocity initial in the y direction, in this case, is going to be our velocity initial times the sine of the angle. And our velocity initial in the x direction is going to be the velocity times the cosine of the angle. These are going to be independent variables that we're going to actually get to work with. So if I do that, I've got my 100 meters per second times the sine of 35 degrees, and I've got 100 meters per second cosine of 35 degrees. And if I plug that into the calculator, this gives me 57.4 meters per second. This one gives me 81.9 meters per second. So I can actually plot that, put that in my picture. We know that this part is going at 81.9 meters per second, and we know that the y part is going at 57.4 meters per second. We also have some tools in the toolbox, right? We got some tools in the toolbox. We know that the change in y is going to equal the initial in the initial in the y direction. Gravity is pointing down, although we also know that the coyote and gravity have an interesting relationship. So, sometimes gravity works, sometimes it doesn't for the coyote, but we got that part. So there's my minus 1/2 gt squared. Well, we know what the change in y is, right? Because we want to end up 500 meters below where we started. I know what my initial velocity is. I know what gravity is. The only thing I don't know is the time. And we're kind of wanting to know how long we got to have the Roadrunner stand there. Okay, we got to kind of know how long the Roadrunner stand there. So one of the things I can do is I can set this up. So I'm going to move this to the other side, right? I'm going to move this to the other side. So I'm going to get g over 2 t squared minus the initial velocity in the y direction times t. And I'm going to have my minus change in y is equal to 0. And this is going to be 500, and the minus comes from the fact that we're going down. This minus comes because I came over here and my initial velocity was going up. So now I can plug in numbers. I can get 9.8 divided by 2 t squared minus 57.4 times time minus 500 is equal to 0. Well, I can do a couple of things at this point. It just depends on what you want to do. Okay. Me, I'm going to take the simple way out. I'm going to remember that the quadratic equation, so I might want to put the quadratic equation on my cheat sheet. It's minus b is plus or minus the square root of b squared minus 4ac all divided by 2a. So that's going to give me my two solutions to my quadratic equation. And so I'm going to plug in my numbers. Okay, I'm going to plug in, this becomes minus 57.4 plus or minus the square root of 57.4 squared minus 4, 9.8, c is a minus 500, all divided by 2 times 9.81. And now it's a plug and chug into the numbers. So let's plug and chug. Oops, I forgot a 2. There should be a 2 there. 9.8 divided by 2, 9.8 divided by 2, because my A is 9.8 divided by 2. Okay, so so now I get minus 57.4 plus or minus So I'm going to get my 57.4 squared. This is 3295. I'm going to end up with a plus, right? I get 2 times 9.8 times 500. This ends up being 9,800. If I've done my punching into the calculator right, these two cancel, so I get 9.81. And you guys let me get away with it. Nope, that's okay. That minus is all right. That minus is okay. But that minus should be a plus. Everybody see where I made the mistake? Okay. So now I got the square. That's also why it's nice to go back and, or when you're doing these things and putting them into the calculator, to write down your individual steps, because then it's easier to figure out where you might have screwed up. So this is 13,095, 9.8, and this is 57.4. So I end up with 57.4 plus or minus 114.4 divided by 9.8. So in one case, plus 57.4, I get 171.8 divided by 9.8. And that gives me 17.5, and this is all it's going to be in seconds. Now, I don't have to do the other one. Why?
Because it's negative, you can't have negative seconds.
I can't have negative time. So I've got this one. I've got 17.5 seconds. So that's how much birdseed I'm going to have to put out there, depending on the rate that the Roadrunner decides to eat the birdseed, to get down. Now the question becomes, if I place this 2,300 meters away, is it going to be, am I going to hit the target? Because the next question is, how far from the edge of the cliff do I actually have to be? Well, that's easy enough, because now I got the time, right? Because if I got the time, we know that the distance is going to equal the velocity in the x direction times time. We know that the velocity in the x direction is 81.9 meters per second. And we know that it's 17.5 seconds is going to be where we're going to get there. And if we do that, 81.9, I'm going to hit 1,436 meters away. And so if I set my birdseed at 2,300 meters, I'm going to miss. I'm going to end up, let's see, 1,400. I'm going to end up about here when I wanted to end up about there. Which is usually what happens to the coyote, right? Either that or the rocket explodes at the top of the ramp, or he misses and he hits the spot in another spot. You know, we know what happens. So then the question becomes, what velocity do I have to have in order to be 2,300 meters down the road?
He needs a miss one black to help.
Well, have you ever seen the ones where he's got the little projectile motion on there? Okay, he's got on the screen, he's got his projectile motion thing. So now we find out how much rocket fuel do we have to have in order to get up there, so we can actually calculate that. So let's figure that out.
Hold on, for 81.9 times 17.5, you got 1,436.
That's what I punched in.
My calculator's giving it to me wrong.
Let me try it again. 81.9 times 17.5. This time I got 1433. I carried an extra digit, so that's in my calculator.
Oh, that's what I got.
Yeah, the 1433. Yeah, well, I'd left the time in my calculator from the previous and I'd rounded it. So, but let's go back and let's figure out what he has to. So if I want to be at 2,300 meters, I need to know the velocity in the x direction times the time. Well, that's 2,300 meters divided by the time, which was 17.5 seconds. So we need that. So if I do 2,300 divided by 17.5, I end up with 131 meters per second in the x direction. That's Vx, but Vx is equal to the velocity times the cosine of the angle. And if I have my ramp at 35 degrees, I get velocity x divided by the cosine of 35 degrees. This is going to be 131 divided by the cosine of 35, which is going to give me 160 meters per second. So in order to go the distance, I've got to add some rocket fuel in order to get me the 160 meters per second. So you can play with these. These are a lot of fun to play with. Now here comes the really fun part. How many golfers do I have? Anybody play golf? You guys over in Enid? Anybody play golf? No golfers. I got some golfers. Okay? Guess what? You're doing this in your head all the time. Because if I have my irons, right? These are my irons. Turns out, kind of interesting thing, there is no set. Whether if I have Callaway clubs or TaylorMade clubs or Callaway's TaylorMade's, what's the other big one? Titleist. It doesn't matter. If I have clubs, the range of my irons is not standardized by the United States Golf Association or the World Pro Golf Association. So if I have TaylorMade's, my irons are going to have different angles than my other ones, my Callaway's or something like that. They're in a good range. They're usually running from about 5 degrees to 25 degrees, but your irons aren't all at the same angle. But that's what's happening with my iron, because here's my little tee and there's my golf ball, right? And so you're choosing your iron in order to hit whatever, there's the little mound with the little flag on it. So you guys are calculating projectile motion based on your regular swing. How hard do I have to hit it? Which iron angle am I got to be at in order to get my ball to land where I want it to do so? So you guys are doing projectile motion all the time. With baseball players, you're doing projectile motion all the freaking time when you're throwing that ball. Now, the other part of it, the part that we have discounted is the pattern that the ball is going to follow, okay? Because we have fluid dynamics, it's going to create the change of what's happening with the ball. If I could just, basketballs are pretty easy. There's not a whole lot of fluid dynamics that's changing a whole lot of the basketball. Other than if it hits the rim, is it going to circle around the rim? My golf ball usually is set up so that I'm going to get a nice aerodynamic pattern that's going to fly a little bit straighter. What the problem with my pitchers are, that's what the seams of those balls do on there is going to give me why I'm going to get a knuckleball versus a fastball versus a sinker. Okay, that's all the fluid dynamics part of the ball. But just throwing the ball to get from first to third, you're doing projectile motion based on what you know your speed of your ball is going to be. And basically what you're trying to do is throw it fast enough that it's not going to have any drop, unless you're trying to get it to the catcher at home plate, where you do want it to have that drop, right? But you're doing that calculation in your head more often than you know. So I always laugh and say people do more physics in their head than they ever can write down on a piece of paper. Because you've been playing with gravity all your life. You've been playing with it all there. Now the really fun part is if you're an equestrian. Not only are you doing the physics for yourself, you're doing the physics for your horse. When does the horse have to take off before the horse goes over the jump? And you have to know your horse in order to how it's going to go over the top. Okay? So it's just something that we all do and we think about and we're actually working on it. Let me see. We're about to lose everybody. I've got it's 2:20. I timed this perfectly today. Woo!